welcome to the final video in the Prove It series on probability. You might have heard, or you may even know from first-hand experience, that the interviews we give our potential traders at Optiver are on the challenging side. But, like many of the puzzles we've solved in this series, you already have the tools for success in your hands. You just have to be able to wield them quickly, accurately, and creatively. To be able to do this requires experience. As such, the best way to prepare yourself is to practice problem solving, particularly in the realm of probability and decision making. Today, let's finish the series with a few practice interview questions. These aren't as complex as some of the problems we've encountered, but remember, in an interview with the lights turned on you, you might feel the heat. In each of the questions I ask, remember to pause the video and have a go at solving it yourself. Let's start with this one. What is the probability of rolling 6 dice and getting exactly one of each number? Before you scan your brain for some archived formula, simply picture the scenario. Actually, imagine rolling the 6 dice and getting one of each number. Straight away, you feel the chances are very small, and you can showcase this intuition to your interviewer. Great, they say. Now please provide an exact answer. It's always a good idea here to think out loud, and maybe it comes out like this. Well, I'm going to roll 6 dice and I want them all to be different. It doesn't matter what the first dice is, but the second dice must be different to that, and there is a 5 on 6 chance of this. Then the third dice must be different to the first two, and there is a 4 on 6 chance of that. If I continue in this way, I will get that the probability that all are different is equal to 5/6 times 4/6 times 3/6 times 2/6 times 1/6, which is just 5 factorial divided by 6 to the power of 5. Okay, the interviewer will reply, and what is this equal to as a percentage? This is a vital step. Why? Well, a percentage probability is something you can grasp and make decisions on. As an analogy, imagine that you found the most incredible mathematical formula for pricing the instruments you trade. Ultimately, it needs to produce actionable numbers, so it's no good if it gives you prices dressed up in garments made of hypergeometric functions. Your response might be, but don't we have computers available? Don't we ever? But the analogy carries there too. Some of the formulas we use are so complex that there are times that we need to reduce them to a simpler form so that even computers don't plod too slowly with the number crunching. In these cases, it is a human, a trader or a researcher that takes the complex thing and transforms it into something that can produce results faster. Now, this process, making complex things simple, is precisely what we are assessing when we ask you to express 5 factorial over 6 to the 5 as a percentage. And that's enough stalling. How would you do this? Well, you should be able to work out that 5 factorial is 120. And so you have 120 over 6 to the power of 5. And you could write 120 as 6 times 20, and then you can cancel this 6 with one of the 6's on the bottom. This gives you 20 over 6 to the power of 4. Now, you start thinking about the powers of 6, and you realize that 6 to the 3 is 216. And this actually helps us a bit, because we can say that 20 over 216 is close enough to 20 over 200, which is just 1 over 10. Now, this approximation might endow a pure mathematician with goosebumps, and not the good kind, but this sacrifice in precision allows us to proceed at pace. So the answer is about 1 over 60, which is about 0.016. You are expected to be able to make those conversions, and this gives you 1.6%. FYI, the actual answer is about 1.5%. So you need to know your basic probability stuff well, and you need to be able to convert your expressions quickly, often mentally, to a number. I'll say it again, practice. Now, that one was the kind of problem you might see in a textbook. It's fairly linear and not too hard to go from problem to mathematical expression to number. Here is a different example. If I roll 3 dice, what is the probability that the sum is a prime number? Now, this is the kind of thing that some candidates struggle with. For sure, if you cling too tightly to your textbook approach and start considering all of the enumerations of rolling 3 dice, then this is going to A, take forever, and B, become quite complex. My tip here is to relinquish your textbook grip and relax your mind. We will have to use street fighting mathematics, as this is one of those questions where being precise will hold you up too much. Let's think big picture. When rolling 3 dice and summing, the possibilities are the integers from 3 up to 18. That's 16 possibilities in total, and the primes are 3, 5, 7, 11, 13, and 17. There are 6 of them, and they are somewhat distributed uniformly here, as in they aren't all clumped together. And the overall distribution is fairly smooth, in a discrete way, and as such, 6 on 16 is a perfectly reasonable answer. Again, you might get asked for a percentage. Here, 6 on 16 can be reduced to 3 on 8, and this is 3 times 0.125, which is 37.5%. The actual answer is about 34%, so we're pretty close. But imagine counting all of the different combinations. It would take many multiples of the time we took. For this problem, and for many others, sacrificing precision for time is a great trade. All right, let's do one more. You've got a 6-sided dice. What is the probability you roll the same number twice in a row? That's not too bad. The answer is 1 on 6. But what if I tell you that the dice has a chip in it, and the probabilities are not uniform anymore? Does the probability of rolling the same number twice increase or decrease? The answer is that it is more likely now to roll the same number twice in a row than it was before. But how can you draw this conclusion in an interview? You could start with an extreme example. Imagine that now there is a 50% chance that the dice lands on 6, with the remaining 50% spread across the other 5 numbers. Then there is a 1/2 times 1/2 chance, or 1/4 chance, of rolling 2 6s in a row. And therefore, this is a lower bound for rolling 2 of the same number in a row. This is already greater than 1 on 6, so I now have some evidence that the biased dice is more likely to show the same number twice in a row. Can we reason more mathematically? We can. Let's have a go. Let us assume that the 6 faces of the dice respectively have probabilities P1, P2, and so on up to P6. The probability of rolling the same number twice in a row is the sum of the squares of these probabilities. Now, imagine for a second that all the probabilities are the same. What happens as we start to perturb this? Say we increase one of the probabilities by epsilon and decrease another one of the probabilities by epsilon. The expression becomes this one. Now, when we expand this out, we get the original expression, but increased by 2 times epsilon squared, which must be a positive number, and therefore results in an increase to our original probability. Thus, we have acquired more gravity for the hypothesis that a biased dice is more likely to roll the same number twice. Now, I'm pretty happy with the above in an interview, but if you like, you can use the Cauchy-Schwarz inequality to put the problem to bed. Indeed, this inequality states that for sequences of real numbers, a1 through an, and b1 through bn, that this inequality holds. If we let the first sequence be our dice probabilities, and the second sequence just be a bunch of 1s, then the inequality reduces to this. Notice that I have removed the possibility of equality. We are allowed to do this with Cauchy-Schwarz whenever the 2 sequences are not scalar multiples of each other, as is the case here. Also, the sum of the probabilities is 1, so we now have that the sum of the probabilities squared is greater than 1/6. And therefore, we have now mathematically shown that rolling the same number twice on a biased dice is more likely than on an unbiased dice. Hopefully, you're getting a good picture from the 3 problems we've looked at, but let's summarize some interview tips. Know your probability, statistics, and mathematics well. But don't always look for a tool to apply. Think intuitively and practically about the problem. Sometimes this is all you need. Practice reducing complex problems and expressions to simpler versions. Finally, don't just give an answer. but try and prove it relative to the conditions of the interview, which typically might just involve thinking out loud and providing some justification. Before I go, let me give you a sample interview question to try after the video. You can send in your solution to this, specifically how you would go about solving it in interview conditions. If I roll 5 dice, what is the probability that the sum is equal to 15? Try and find a solution or method that nicely balances precision with speed. And one more thing for you to send along with the above. Can you provide a simpler but still concrete proof that you are more likely to roll the same number twice on a biased dice? Good luck and goodbye.